mentions Khovanov-Rozansky homology. And then I'll talk a little bit about general structures, like what do we expect about some kind of general structure of this homology, how it's related to other homologies like Khovanov homology that many of you know better, or SLN homology. And then in the end of the talk, I'll mention some geometric models for some classes of links where we can actually use algebraic geometry and say that basically Khovanov-Rozansky homology is homology of some space up to some technicalities. And so I'll explain that space and why this space actually might be of interest to many of you. And there are some interesting connections to contact and symplectic topology. Okay, so that's the plan. And so the first thing is like, what is a Homfly polynomial? I think most of you have seen this before, just a reminder. So it's a invariant of links defined by scaling relations. So if I see a link diagram, if I see a piece like this or a piece like this, or a piece like this, there is a linear relation. And it's kind of not standard normalization, and I will be kind of sloppy about normalization anyway. So you can put A here and A inverse here, or you can normalize by the right, and you get this, but it doesn't matter that much. And then if you have a separate circle, which is kind of disjoint from the rest of the diagram, you put this factor, A minus A inverse over Q minus Q inverse. And if you have a curl, that's kind of this non-invariance in the first line, means that the first Rademacher moves actually adds a factor of negative A inverse in this normalization. And it's a standard fact that if I have any oriented link diagram on the plane, I can use this rule to simplify it until the links become trivial, compute the Homfly polynomial inductively, and then it doesn't matter how I simplify the diagram, so it's actually up to some power of A again, because I use this non-standard normalization. So that's clear. And then, oops, is it me? 1 second. Close something. Okay, yeah, so then Khovanov and Rozansky use Homfly polynomial as a starting point, and they define a triply graded link homology. So it's a kind of very complicated machine. So you input a link diagram again, and then you output a triply graded vector space H with 3 grading I, J, K, usually related, denoted by Q grading and A grading and T grading. So the first 2 gradings are related to Q and A in the Homfly polynomial, and the third grading is homological. So if I take the Euler characteristic with respect to the third grading, I get back a function of Q and A, and this agrees with the Homfly polynomial. And so in this sense, just as like the usual Khovanov homology categorifies Jost polynomial, this homology categorifies Homfly polynomial. And the actual definition is very, very complicated, and we definitely won't need it. It uses theory of Zorgel bimodals, it uses Hochschild homology. You can phrase it purely in the language of like commutative algebra and computing homology of a very complicated complex over a polynomial ring. But we won't need any of this because that doesn't help at all, I'd say. And kind of technical remark, so for Homfly polynomial, the way I defined it here, it's actually not a polynomial, it's a rational function in Q. And you can, if you have a knot, you can always normalize this rational function to get a polynomial. And the same way you can normalize your homology to have a finite dimensional homology. And that's what I will be using most of the time. This is called reduced Khovanov-Rozansky homology. But I will mention at some point unreduced homology as well. And if you have a link, there is no hope to have something nice and finite dimensional here. So you will, for links, you would expect infinite dimensional homology groups. And I will show you some examples there. But of course, like if you want to study combinatorics, it's much more complicated to define combinatorially what is an infinite dimensional space. Okay, so any questions? Okay, all right, so what do we actually know? So kind of general picture is that so for 2 strands, you can just do it by hand, and any node or link that you can get on from a 2-strand braid, you get T2N torus link. You can compute the answer, it's not hard. And then any other example is super hard. So as long as you go from 2 strands and 3 strands, you get like a very hard computational problem. So it's a complex of modules over a polynomial ring. The number of variables in a polynomial ring is the number of strands in the braid. And then the number of terms in the complex is exponential in the number of crossings, because each crossing gives you kind of two-term complex, as in Khovanov homology. And nevertheless, I want to advertise a recent paper by Keita Nakagane and Takeshi Sana. So they actually wrote computer program computing this homology. And so they computed HOMFLY homology for all nodes with at most 10 crossings and most 11 crossing nodes. I think there was some kind of restriction on the number of strands where you can write this node as a closure for braid. But it's a lot of data. It's several hundred nodes. Here, I'll say exact numbers in a second. And basically, if you give me a node from a node table with 10 crossings, now there is this output of their program which says this is the node homology. And so there is a lot of data to be explored. And I think one basic goals that Alex and I were thinking about it just, okay, so we have several hundred nodes. How do we understand any structure in their homology? Like, can we make sense of this data set? And I'll show you some examples. Okay, so here's a typical example. Here's the node 11A85 from the node table. It's a two-bridge node. And so, as I said, homology is triply graded. So you have three gradings, A, Q, T. And the first basic question is, how do you actually visualize this? So you have three gradings. So you have kind of three-dimensional space of things. And at each grading, each tri-grading, you have a vector space of some dimension. And so one idea, which goes back to Jake Rasmussen, is to use some version of delta grading that appears in many different contexts. In this context, and in some normalization, delta grading is just the sum of these three gradings here. And it turns out that for many nodes, this delta grading is very constrained. And so in particular for this node, everything is supported in one delta grading. And so what's written here is that, so delta grading is fixed to be 2 in this example. And then the Q grading is horizontal, A grading is vertical, and then these colored numbers are just dimensions of the homology groups that you see. So for example, in Q degree 0, A degree 4, you see a 12-dimensional Khovanov-Rozansky homology group. So that's the output of this program. Okay, and again, it's kind of maybe surprising, maybe not so surprising that everything is in the same delta grading for this particular example. Okay, but the homology is huge. So there are like the total dimension of homology, I don't even know what it is. So you need to add all these numbers. And even if you look at this picture, you see lots of nice structures. I'll talk about this, but it's clearly symmetric around the vertical axis. The numbers kind of grow to the middle. And this is not kind of a random arrangement of numbers. And I'd say it looks better than many pictures you see in Khovanov homology, to me at least. Okay, and so basically, like, I mean, one thing you can do is just produce tons of such pictures from this data set. And in this case, it will be supported in one delta gradings. In some other cases, there will be more, but you can kind of slice by delta grading, and in each slice, you would get a nice picture like this. Okay, and so in this example, I said this is a two-bridge node, and there is an old result of Jake Rasmussen's that actually for all two-bridge nodes, HOMFLY homology is supported in a single delta grading. And so as a consequence, you can actually read off these numbers from the HOMFLY polynomial, because so the T grading is determined by the A and Q, if you know that the total sum is fixed. And so if you know A and Q, you know kind of the parity of the T grading. And so up to signs, these numbers are the coefficients of the HOMFLY polynomial. There are no cancellations if you take the Euler characteristic. And so the HOMFLY polynomial is just the sum of these terms with some signs depending on the parity of T. Or like, this is probably not standard T, but whatever. Okay, but this is cool, but I want to emphasize that if you just know that this is determined by the HOMFLY polynomial, it doesn't explain this nice structure. So I think there is more to this that you couldn't see from the HOMFLY polynomial. Maybe some things you can see, but like the fact that things kind of, for example, grow to the middle, it wouldn't be easy to explain from just the combinatorics of HOMFLY polynomial, but I'll try to explain why this works from HOMFLY homology. Okay. Any questions? Cool. Yeah, so this is a nice example. Here's another example. So this is a node 11A263. Again, another big example in the node table. It's actually a pretzel node, I think. And in this case, it's supported in 2 delta gradings. So delta grading is equal to 6 and delta grading is equal to 8 here. So there are just 4 different gradings with 1-dimensional homology in degree 6, but there are lots of them with lots of interesting properties in delta grading 8. And everything is supported in 2 delta gradings. And so again, it goes back to actually work of Rasmussen, and he noticed in the same paper when he proved that 2 bridge nodes are in the same delta grading, is for most alternating nodes, the HOMFLY polynomial is supported in a single delta grading. You can just compute it, you can scan through the data set, and we checked it with this new data that wasn't available to Jake, and yes, indeed. So for all nodes in the data set, except for this particular one, the homology is supported in a single delta grading, and this node is special by some reason, and this is supported in 2. And I think it's very much an open question, what makes it special? Like, if I give an alternating node, do you know if it's supported in a single delta grading or not? How to compute HOMFLY homology of alternating nodes and links in general? And I think, again, we know how to compute Khovanov homology and some other homology, and I think it's interesting that for HOMFLY homology, you see some new phenomena. And I think just what makes it special, I don't know. And I think it's a good open question here. Okay. And it turns out that in this data set, because the nodes are kind of too small, all nodes are supported in at most 2 delta gradings. So lots of them are supported in a single delta grading. If you look at this table at the bottom, so there are 600 nodes in a single delta grading. Some of them are 2 bridge, some of them are alternating and not 2 bridge. And there are lots of other nodes which I don't know how to characterize, but they're all supported in a single delta grading. And then if you look at 2 delta gradings, so there is 1 alternating node which we saw on the previous page. And then there are 91 more which are supported in 2 delta gradings, which we need to understand somehow. And this, on top of the page, you see a bigger example of a node 11 and 80, where you have kind of something substantial in both of these delta gradings. But again, the numbers look kind of nice and regular and symmetric in many different ways. Okay, so this is the data that you get just from directly computing this homology. And maybe, I mean, one more thing that I want to say about the data set is people try to compute it before. I think Ben Webster wrote some programs, but the main issue was that you have to work with these modules over polynomial ring. And I think they quotient by the, because this is reduced homology, you can quotient by this polynomial action, and like they managed to quotient it efficiently and kind of reduce it to computation with this finite dimensional vector spaces. That's kind of one of the progresses, but again, I didn't really know the specific algorithm that they did, but the output is very nice, and this you can just produce from their data. And maybe one more thing that I forgot to mention is that all these nice pictures are, of course, drawn by Alex Chandler, who knows how to draw them, and I don't. Okay. Anyway, any questions? Okay. So if there are no questions, I'll go to a different source of examples, which attracted a lot of attention in last 10, 15 years. So these are torus nodes, and in particular, what is the HOMFLY homology of torus nodes? And here is an early example. So this is a 3-4 torus node, and it's HOMFLY homology. And I've taken this picture from a paper of Gukov, Dunfield, and Rasmussen, which is also quite old, around 2005, maybe 2007. The picture has lots of nice structures. I'll try to explain most of them like in the course of this talk. So the data is presented slightly differently. So here each dot represents a homology generator. And the numbers, so the Q grading is still horizontal, A grading is still vertical, but the T grading is represented by these numbers. And there is some slight regrading, which I'm skipping. You can check that for this node, everything is in 2 different delta gradings. And this is one of the nodes in the data set, I think 819, maybe. And what is important is that each dot represents the homology generator. You can look at all of them together and kind of smash all these different layers with different delta gradings together. And so then you would have 5 generators in A degree 0, 5 generators in A degree, I mean, it went in the bottom A degree, let's say 5 generators in the middle A degree, and 1 generator on the top. And so total dimension of homology is 11. And again, here we just slice it by the A degree, we ignore the delta grading because that could be more complicated in general. In general, for torus nodes, if you increase the node, that you can have like arbitrary many delta gradings, and it will be, I think, quadratic in these parameters of the torus node. Okay, and then one question which lots of people ask is, okay, so you have these numbers 5, 5, and 1. So the dimensions in each row of this homology, have we seen these numbers before? And if you like combinatorics, you can observe that there are 5 ways to triangulate a pentagon. So 5 ways to draw 2 non-intersecting diagonals in a pentagon, 5 ways to draw just 1 diagonal, and 1 way to draw no diagonals. And in total, again, you have 5, 5, and 1. So you could imagine, maybe, that on the bottom row, the terms or the generators of homology are parameterized by triangulations. On the next level, they're parameterized by kind of partial triangulation when you have only 1 diagonal. And on the top, you have no diagonals at all, and there is only 1 such diagram. Okay, and maybe you've seen this in combinatorics, that the number of triangulations on the bottom level is called the Catalan number, and there are some formulas for it. We won't really need it. And so the conjecture is that's always true. And so I have conjectured this in around 2010, and Matt Hogancamp and Anton Mellit actually proved this conjecture in increasing generality, and then they proved this in full in 2017. And so combining their theorems, we get the following results. So first of all, the total dimension of HOMFLY homology for n plus 1 torus nodes, so not any torus node yet, but just n plus 1. And the total dimension is equal to the number of partial triangulations, or the number of ways to draw some number of non-intersecting diagonals in the n plus 2 Goa. So before we had 3, 4 torus node, and we drew diagonals in the pentagon. So 3 plus 2 is 5. And this is just the total dimension. You can actually refine this and read all the gradients from the combinatorial side. So in particular, if you look at the bottom row, kind of A degree 0 part of HOMFLY homology, this is equal to so-called QT Catalan number, which I will define on the next page. And then more generally, the bigraded dimensions of the bottom row are given by so-called rational QT Catalan number, which can be defined for any m and n, so for any torus node. And in principle, they have a more general result how to describe higher levels, but they're a bit more technical and hard to phrase. But I think the outcome of this theorem is we actually know how to compute HOMFLY homology for all torus nodes. And as far as I know, we don't know how to compute Khovanov homology for torus nodes. And I'll say a couple of words about this later, but I think in this way, this is very strong result. Question? Okay, and kind of side remark for people who like torsion. So all this is over Z, so actually homology is free. There is no torsion in these examples for torus nodes. That's part of their theorem. Okay, and so what is QT Catalan number? Again, like kind of really brief introduction because it's not combinatorics talk. So QT Catalan numbers have been studied by lots of combinatorial people. In particular, Francois Bergeron, Adrian Garcia, Mark Heyman, Jim Haglund, many other people. There's a lot of activity and related to lots of complicated things in algebraic combinatorics. The shortest definition is the following. So you look at the rectangle M by N. So let's say M is vertical and N is horizontal. You draw the diagonal in this rectangle, and you count the latest path below the diagonal. So if your rectangle would be a square, this is one of the definition of Catalan numbers, and it's known that these dict-paths are in bijection with triangulations. That's right. Here you can put any M and N. If they're co-prime, there are no integer points on diagonal, and so there are nice formulas for latest path as well. And so this QT Catalan number, you can define it as the generating function for such path, weighted with two statistics called area and div. And area is, roughly speaking, the area below the path, or more precisely, the area between the path and the diagonal. And div is something much more complicated. But in any case, it's something very explicit. You sum over all these paths, and you get these QT Catalan numbers. And so in particular, you can rephrase the theorem on the previous slide, that there is a basis in HOMFLY homology for torus nodes labeled by this dict path, and each dict path lives in some very specific grading prescribed by these combinatorics. And so in this sense, we know actually a lot about homology of torus nodes. Okay, and again, there were lots of papers and lots of conjectures around this, but I think the summary was, so this was summarized and finally proven in this series of papers by Matt and Anton. Okay, so for torus nodes, this is kind of a different set of examples. We can't really analyze delta gradings, but we know it from very different perspectives. Okay, and then, so next I want to talk about some structures. What do we know in general about node homology? And so the first kind of structure, which you might have seen in the pictures from before, all of them, that the homology is actually symmetric around the vertical axis. So it's not symmetric around the horizontal axis. If you mirror the node, you flip it in the horizontal axis, but it's always symmetric around the vertical axis. And this reflects the symmetry of the HOMFLY polynomial when you fix A, but you change Q to Q inverse, which is known. And only last year, in a joint work with Matt and Anton, we proved that for any node, this is actually true. This was again conjectured long time ago by Khovanov and Anton Mellit, that you have the symmetry, and moreover, there's an action of the Lie algebra SL2 in HOMFLY homology, which yields this symmetry for absolutely any node. And so if you know something about finite dimensional representations of SL2, you know that the characters are always symmetric and the representation is symmetric in some precise sense. And also the dimension of different graded components always grow to the middle. And so in particular, this implies that the data that we get from any of these computations will be symmetric and grow to the middle in the horizontal direction. More precisely, so for torus nodes, this would imply, for example, that this QT Catalan number is symmetric in Q and T. And I didn't define for you these two statistics, but the formula was Q to the area and T to the div. Area and div are two very different statistics. It's an open combinatorial problem to prove this combinatorially. There are kind of hard algebraic proofs of this fact by now, but it's not obvious at all that this thing is symmetric in Q and T. And you can prove it using knot theory if you want, but that may be an overkill. More practically, so this action of SL2 is kind of acting horizontally. It preserves the delta grading. So in the previous pictures from this data set of Nakagami and Sano, you can just like look at one single delta grading, focus on that. And it also preserves the A grading. So SL2 would act in each row separately. So maybe I can go back. So in this example, SL2, for example, would go to here, from 0 to here, then to here, and then to there. And then this guy would be a separate sub-representation of SL2. Here it would go from here to here to here, and then to here. So there will be two different representations here, and then this is just one-dimensional representation of SL2. And another thing that you might know from representation theory of SL2 is that the dimensions grow to the middle, as I say, and this is true in every single delta grading, in every single A grading. And so the rank of HOMFLY homology grow to the middle except that they grow kind of in each parity. And so maybe I'll show one example from the slides. This one. So for example, you look at this row, so you see that SL2 in this picture would go from 1 to 4, 4 to 6, 6 to 4, and 4 to 1. So that's one part of this. And then dimensions grow to the middle. There is a separate part, 1 goes to 3, 3 to 1. That's a separate part with kind of odd weights for SL2. And you see that they grow to the middle, but something depends on the parity, or I guess in this case, in this normalization Q mod 4, they would grow slightly different just because the SL2 jumps over two places, as it does classical. And so that's how this works. And again, it works in every row, in every single delta gradient. Okay, so this tells us something general about this representation, which is not kind of obvious at all, and it's not obvious from definition of HOMFLY homology. Okay, so the next question I want to talk about is about unreduced homology and links. So I want to mention briefly some things. So the main problem is that for links, the unreduced homology is always infinite dimensional, and the HOMFLY polynomial is always a rational function in Q, which you would need to expand as an infinite power series in Q. And naturally, HOMFLY homology is a module over the polynomial ring. So on each component, you can put a marked point, and there's an action of the homology of unknot on homology of the link, but this action depends on the choice of marked point, and so you can choose a marked point on each component. All these different actions would commute, and this would lead to an action of this large polynomial ring on the link homology. And if you want some kind of symmetry or SL2 like on the previous slide, you can't do it directly because the symmetry doesn't preserve this xi, it doesn't preserve the degrees of xi. And kind of motivated by this problem and to fix this problem, so Matt and I defined the deformation or so-called yification of HOMFLY homology for links which depend on some additional variables y1 through yr, of which are different degrees from x's. And then we proved that this yified homology is actually symmetric, and you can define SL2 action, which in some precise sense changes x's and y's. And so the yified homology in this sense is better than non-yified homology. And I have to say that this is like the important distinction is only for links. So if you have a knot, then actually unreduced homology is a free module over homology of unknot by the old result of Jake Rasmussen again. And so this yified homology is just the reduced homology that we've been computing times polynomials in x and y. So if this thing is symmetric, you can quotient by cx and y, and this reduced thing will be symmetric. And so in this sense, yification or going to unreduced homology actually doesn't give you any new information. But for links, you get a lot of new information, and this is kind of, I think, the better way to think about link homology, to capture these things. And maybe for experts in the audience, like one source of this y variables is related to monodromy of the fixed points. So you can say that the action of unknot, of the homology of unknot on homology of the link depends on the choice of marked point. And then you can take this marked point and drag it around the component. And this leads to an interesting monodromy. And you can use this. So this monodromy would be an interesting chain map on the corresponding chain complex. And you can use this to deform the differential and define this yified homology. And maybe I don't want to say more, but again, I think it's an interesting construction. And one specific example, which is dear to my heart, is that you take the n torus link. So this is just n unknots, like n fibers of the whole fibration. So you have n unknots pairwise linked. You have n components, so you expect an action of large polynomial algebra. And so what we proved with Matt is that actually you can explicitly describe the yified homology. The yified homology is the following thing. You take polynomial algebra in n x variables and n y variables. Inside this, you have this ideal G, which is the intersection of ideals where xi generated by xi minus xj and y minus yj. You intersect over all pairs I not equal to j. This has some kind of algebraic geometry meaning, but let's not talk about this. But it's some very, very explicit ideal in this polynomial ring. Because it is an ideal, it's a module over x's and y's. And the theorem says that the homology of n torus link is actually isomorphic to this ideal. So it's clearly infinite dimensional, it's clearly a module over x's and y's. And also it's clearly symmetric in x and y because we just computed it, it's symmetric. And again, yeah, that's fine. So you can think of this xi minus xj and y minus yj as the equation for diagonal and c2 to the n, but maybe that's not so important. And this is the y-fied homology. So if you want to go back to HOMFLY homology, you need to quotient by the y variables. And in this particular case, you can check that the homology is free over y's, and the quotienting somehow doesn't destroy nice properties. Okay, so this is kind of a different type of answers. I don't give you a basis. So Matt and Ben Elias, they have a separate paper when they give you a basis and they give you a combinatorial formula for this thing, but somehow that is much more complicated than just writing this answer. And in this sense, I would say that y-fied homology is easier to understand because I don't give you a basis, but I have an alternative kind of commutative algebra description. And if you want to get HOMFLY homology, quotient by y's. And kind of remarkably, I don't know how to describe HOMFLY homology directly without first y-fied and then quotienting by y. And kind of maybe morally, you can say that y-fied is some kind of equivariant version of HOMFLY homology. And so we compute first equivariant homology and then we kill these equivariant parameters. But maybe I don't want to say this precisely. Okay. Any questions? All right. Okay. And so the next structure that I want to discuss is relating this HOMFLY homology and SLN homology. And so again, this is a result Jake Rasmussen, that there is a spectral for each n, capital N, there is a spectral sequence from reduced HOMFLY homology to reduced SLN homology. And in principle, you can do unreduced, but unreduced HOMFLY is infinite dimensional. We don't want to do this. And this spectral sequence, so you have 3 gradings on HOMFLY homology. You have 2 gradings on SLN homology, and so the Q grading on SLN homology is collapsed. It's like Q plus N times A grading. So there is some kind of regrading and collapse of 3 gradings into 2. And so here is a kind of easy example when you can do everything by hand. So here is the Note 911. Here is its HOMFLY homology. Again, it's supported in a single delta grading. And so in this case, suppose that I want to compute SL3 homology. So you can check that the spectral sequence, all the differentials would actually change the delta grading in this example. And so in particular, because everything is single delta grading, all the differentials in the spectral sequence must be 0. And so nothing happens. There are no differentials in the spectral sequence, but there is this kind of ugly non-trivial regrading, which leads to the picture on the right. So I mean, kind of if you tilt your head and think a little bit, you can kind of recognize this picture and the picture on the right. And I think I swapped the axis Q and T to save the space. And I think this is the picture that many of you are familiar with in SL3 homology and SL2 homology. I think this picture is actually taken from Lucas Luerk's computations of SL3 homology. So he has a program computing SL3 homology. But I'd argue that in this particular case, it's much easier to compute HOMFLY homology, which is nice and symmetric as we discussed, and then just try to compute the spectral sequence. In this case, it collapses and you get this result on the right. So in this case, we just understand the spectral sequence and the structure is essentially the same, but we just organize it slightly more symmetrical. And this leads to lots of questions and observations. So let me mention them briefly. So if HOMFLY homology is supported in a single delta grading, like in the previous example, then actually all the spectral sequences collapses for all capital N greater than 2. So SL2 homology will be the same as a vector space as HOMFLY homology. SL3 homology will be the same, and for all SLN, you just know the answer right away. If HOMFLY homology is supported in 2 different delta gradings, like we saw like for the rest of the data set, then starting from SL3, all the spectral sequences will collapse. Again, it's easy to see. And then SL2 homology might be different in an interesting way from Homology homology in the right examples. In particular, the 3/4 torus knot, and you have interest in differential. And in particular, we actually know, we just look at this data set, we don't do anything, and we know SLN homology for all capital N's, for all nodes in this data set, at least for SL3 and SL4 and SLN. For SL2, we don't know, but comparing this data set with kind of programs computing Khovanov homology would tell us what the spectral sequence is. So there is some gain from there, I think. And there is a special case, n is equal to 1. And so n is equal to 1 corresponds to so-called SL1 homology, which can be formally defined in the same way as all SLN homology, but it's actually one-dimensional for any node. And so this spectral sequence to SL1 is very similar to Lie spectral sequence in Khovanov homology. And so in particular, the degree of this generator in this one-dimensional homology group is related to some generalization of Rasmussen's S invariant. And so then the natural question that we're looking at with Alex is like, can we compute this capital S invariant for all nodes in the data set, or for some nodes in the data set? And can we actually understand this spectral sequence for n is equal to 1? And in many cases we can, and I'll see maybe in a second how. Maybe what is the relation between homological homology and SLN homology S invariant? So for each n, Andrew Loeb, I think, defined lots of interesting invariants, which are kind of versions of S invariants for SLN. And Lurk and Loeb have interesting examples where, for example, SL2 S invariants and SL3 S invariants are different. I think Andrew actually mentioned this in previous talk. This can be explained because, like, you have the same underlying homological homology, but the spectral sequences to SL2 and SL3 kill different things. And I think the expectation, which I don't want to say formally, is that maybe they're different, but maybe we can at least like make a uniform bound for all this like S invariants that they're not too far from HOMFLY S invariant, but that's work in progress. And so maybe in this example, let me see how this works. So the differential, in this case, you can check, because everything is in the same delta grading, that there is only one differential in this Lie kind of spectral sequence. And it goes like this. So it goes from here to here, it goes from here to here, from here to here, and so on. So it goes on these diagonals in the same delta grading. It preserves the delta grading. And so we know that the differential has one-dimensional homology and there are no higher differentials. And so in all diagonals but one, the Euler characteristic is 0, so the differential must kill everything. And then this is the only diagonal where the Euler characteristic is 1, and so there is one homology which survives, and this is in this degree. And so you just kind of visually look at this and you say, well, you know the differentials. And in general, you can't say that, of course. That's the usual problem as with Lie spectral sequence, but in many cases you can. And then there are some tricks that are available in triply graded homology. How do you actually compute this S invariant without doing anything and kind of looking at the data, even if you have several delta gradings and things. Okay, so that's kind of this work in progress. And in this case, I can just identify this guy's the S invariant for the kind of capital S invariant for homological homology. And I think, as far as I know, maybe people would correct me, nobody have ever studied this S invariant except for like Jake, who suggested this 15 years ago for homological homology. And you can ask all sorts of questions. Is it a genus bound? Are there some like interesting properties of it and so on? And I think the main issue was that we didn't have the data, but like now we have a lot of data, so we can ask like how this is related to SL2S invariant, SLNS invariant. Does it give a genus bound? What happens for crossing changes and all sorts of things that everyone likes. Okay. All right. So that's about the spectral sequences. And then the last part, which I'll explain briefly, is about geometric models for knot homology. So I want to construct a space whose homology is effectively Homology homology. And maybe before that, I want to comment that it will be really a single space for each, at least for bottom A degree, and for higher A degrees. I mean, there are some constructions, but they're not really space level as far as I know. And I mean, the big difference with, for example, the work of Lifshitz and Sarkar that Andrew mentioned in the previous talk is that, so they have one space for each Q degree. Here you have one space, but the homology is bigraded. And it is bigraded because algebraic geometry tells you that homology of an algebraic variety carries this extra gradient, which is called the weight filtration. That will be important. So you start from a braid. So the braid group has generator sigma I and the braid relations. So for each generator of the braid group, we write the matrix, very easy one. It depends on one parameter z. So we'll have one parameter for every crossing in a braid. And one can multiply matrices and check this identity that if I have a braid sigma 1, sigma plus 1, sigma I, or sigma I plus 1, sigma I, sigma I plus 1, you don't really get the same matrix, but you get the same matrix if you change the variables. So here you have z1, z2, z3 as the variables. You make some change of variables on the right, and z3 becomes z1, z1 becomes z3, and then you do this weird thing in the middle, but the product of all the matrices remains unchanged. And so in this sense, like up to this reparameterization, we can talk about products of braid matrices and like these z parameters on these products of braid matrices. And then we define the braid variety is following. So we just, if I have a braid, so the braid should be positive. This only works for positive braids. You can do slightly better thing, and I'm lying a little bit here. So this would be positive braid times a negative half twist, strictly speaking, but let's ignore this. So you have a positive braid, you multiply all these matrices, and then you multiply by this matrix with zeros and ones on the kind of opposite diagonal, and you require that the whole thing is upper triangular. So that's some very explicit condition on these. And so this would give you an affine algebraic variety in the space with coordinates zi's, and you have like n choose 2 equations which say that everything below the diagonal is 0. It's very, very explicit algebraic variety. I'll show you example on the next slide.
Are you saying somehow that this doesn't actually depend upon the factorization into sigmas?
That's right. So I'm saying that, so if I choose different factorization of sigmas, if I choose a different braid word, I would have a kind of different variety, but it will be isomorphic to the other one. And the isomorphism is given by the change of variables from the previous slide. So up to isomorphism, the algebraic variety is the same. That's right. And so you can ask lots of questions like, do we know this variety? Have you seen this before? Many of you actually have seen this before, and I'll explain why. But people from like geometric representation theory, for example, Laura Escobar, she actually proved in a different language, and then in a joint paper with Roger Casals, my brother Michael, and Jose Cimental, we translated it to this language, that this variety is either empty, it could be empty. For example, for like trivial braid, this is like never upper triangle. But if it is not empty, then this is a smooth manifold of expected dimension. And if it closes to a knot, then actually you can factor some C star to some power from this variety, but maybe that's too technical. Anyway, there is very explicit variety x of beta, and then you can quotient by C star to some power if you want. And then a big result here is the work which started a while ago by Webster and Williamson. They didn't phrase it this way, and then Anton Mellit rewrote it essentially in this way. And in the meantime, Train finished the proof that if your braid closes to a knot, and I'm lying a little bit about this negative half twist, but it's fine. You can ask me for details. Then actually the A is equal to 0 part, so this bottom row of HOMFLY homology is isomorphic to homology of this algebraic variety, equipped with this additional weight filtration. So that's kind of the hard part, and that's the difference from many other models, that like you have one single space for each Q degree. But the homology of the space has two gradients. You have homological gradient, and you have this additional weight filtration. And so the space is smooth, but non-compact. And kind of the general algebraic geometry says that in this case, you might have interest in weight filtration, and you do. But computing this in examples is an interesting question. And sometimes people do this, sometimes people don't. And so here are two examples. So one example, if you write this braid sigma 1 cube, so you have z1, z2, z3. These are three variables. So this is supposed to correspond to trefoil knot. And then the equations that you get after some simplifications is just you have three variables, one equation, z1 plus z3 plus z1, z2, z3 is equal to 1. And so this is very explicit. I find algebraic variety. It's not completely obvious that it's smooth, as far as I know, but probably not hard to see directly from equation. Its homology can be computed, and they match the bottom row of Homology homology with trefoil. And I have to say that in the same paper of Tring, so he has some recipe for higher degrees, but they're kind of much harder and less geometric. And so one remarkable example of this, where this was taken even further, is the recent work of Pavel Galashin and Thomas Lam, when they identified this variety. So you can define this variety by braid word, but for torus knots, you know the braid word, but you can also write this variety explicitly and connect it to so-called open positroid varieties. And I don't have time to define it properly, but you consider the Grassmannian, so you have M and torus knot, you consider complex Grassmannian M n plus M, and then this is some very specific open subset of this Grassmannian, defined that some minors are not equal to 0, basically. And so this is very explicit variety. You can just define it in coordinates. You can check that this is isomorphic to this braid variety defined by the braid word for the torus knot. And the homology of this variety equipped with the weight filtration are actually given by the same Qt Catalan numbers as I mentioned before. And their proof actually used knot theory. So they were like kind of very roughly, they were saying that the homology of this variety is the knot homology, and the knot homology was computed by Matt and Anton. And so we know the answer. But of course, that's kind of cheating, because if you have an algebraic variety, you can ask, can we actually compute the homology of this algebraic variety directly without doing anything? And like, can we use it to reprove this theorem of Matt and Anton? And I think there are lots of open problems coming from here, but like the state of the art is, we know the answer, we don't know how to actually compute it. In some cases, you can compute the answer directly, and like they and other people in cluster algebras who study positroid varieties, they computed the answer, but kind of there's no uniform recipe for all Grassmannians or all positroid varieties. Like for 3, 4, for example, people computed it using like hard theory of cluster algebras, I'd say. Anyway, and so, right. So the last thing which I want to say is that actually many of you might have seen this equation that z1 plus z3 plus z1 z2 z3 is equal to 1. And this equation comes from so-called augmentation variety of Legendrian knot. So if you have a braid, you can associate to a braid a Legendrian knot in standard convex structure on R3. And a lot of activity in last, again, 10, 15 years was studying Khovanov and DGA for this knot and augmentation varieties. And so if you have a Legendrian knot, which you cook up basically as a closure of this braid, you need to be careful and like explain how you do it Legendrian way, but I don't have time for that. But for any Legendrian knot, Khovanov constructed a DG algebra. The generators of this DG algebra more or less corresponds to the crossings in a braid. So this would correspond to the Z variables from the previous slides. And the differential counts certain philomorphic disks, as usual in the symplectic theorem. And so then the theorem from above says that the braid variety agrees with augmentation variety, means that you take this DG algebra, you compute its cohomology, and in this case of interest, it will be just H0. So basically, you take all polynomials in Z's, modulo the image of the differential, and the image of differential matches these equations that I was writing before. And so the algebra of functions on the braid variety agrees with the H0 with this augmentation variety of this knot. And so for Z2 coefficients for this DG algebra, it was observed by Tamas Kalman a while ago, and then it was upgraded to like Z coefficients and characteristic 0 coefficients by recent work in Casals and Linie N. And so in particular, this braid variety, you can say it's kind of ad hoc construction of matrices, but if you like symplectic topology, it's actually just augmentation variety of some Legendre node. And so it says that intrinsically from this Legendrian picture, you can define it as you have some coordinates corresponding to your crossings in a braid or ripcord, and then the equations correspond to differential from degree 1 guys, and this defines the variety, but then the question is how to actually compute homology of this variety, and that's an interesting question. And so I think it's an open problem to compute homology of this braid variety from directly from DGA, or give some kind of model for this homology, or understand, I don't know, maybe the Ramka homology of this variety, I don't know. But there are like lots of open questions here, but the point is that this variety is not completely random, and it might be familiar to many of you. And like what weight filtration means in cohomology in these terms, I have no idea. Again, it would be great to understand, but in many, many examples, you can just draw this variety and say what it is and how to compute this homology. And I think really briefly, I want to just read this slide and say that there are more geometric models. So this is kind of one which is easiest to explain. There are two more geometric models that lots of people worked on. If you notice algebraic, so it's a link of plane curve singularity in C2. There's a beautiful conjecture of Oblomkov, Rasmussen, and Schende, which give yet another model for HOMFLY homology in terms of so-called affine Springer fibers. I'm not defining anything. For torus nodes, you can actually compute homology directly here. So in this case, you have a different space whose homology is not homology. You can pave this space by cells. You can count dimensions of the cells and get this weird combinatorics. But for anything but torus nodes, the conjecture is wide open, and nobody basically knows how to compute the homology of the space. And so in the cases we know, we just compute both sides and compare. But in general, it's much harder to understand this than braid variety, although it's easier to compute. And I also want to mention that there is a very deep relation between HOMFLY homology and the Hilbert scheme of points on the plane, which is a remarkable algebraic variety, which is a resolution of singularities of a symmetric power of the plane. And there was a lot of work in this direction by myself, Andrei Negud, Jake Rasmussen, Matt, and separately by Oblomkov and Rozansky. So it's much harder to phrase, and I don't have time for this, but like one interesting thing here is that you understand some structures in this model, which would be much harder in some other models. In particular, what does the action of the full twist on a braid do? And so this model is somehow designed to understand what happens if you start from a braid, add a full twist to a braid, and then how the homology changes and how everything else changes. So there is a lot of interesting stuff here, but again, I don't have time for that. And I think the last thing I want to say is that, so if you're interested in the symmetry and SL2 and some other things, we have this paper with Matt and Anton from last year. With Oscar Khovanov and Jose Cimental, we wrote a survey called Algebra and Geometry of Link Homology. So it contains basically everything except for these pictures that we did with Alex. But like all these braid varieties and algebra geometric models for knot homology are there with all details and all references and some many examples. So if you want to know more details, look at that. And if you don't care about algebraic geometry, but you want to see actual computations, so there is this paper of Nakagami and Sana, where they actually compute HOMFLY homology, and they have a link to the data set on some of their web pages. So all this is publicly available, and you can just go ahead and look at what is homology of your favorite knot from the knot table. And I think I'll stop here. Thank you so much.
Other questions for Eugene? I have a question. So, like you identified this HOMFLY homology with like homology of some algebraic variety. Weight filtration. like is which was sort of one of your gradings, is the Hodge filtration some other relevant thing?
No, the Hodge filtration, so it will be always Hodge state. So this variety you can basically stratify into pieces which look like C star to some power and C to some power. So you can prove that the Hodge filtration is always trivial, but the weight filtration is interesting. And so, yeah, I mean, Hodge filtration would give yet another grading, but not in this setup. And yeah, maybe I want to emphasize again that this only works for positive braids. If you have negative braids, non-positive ones, there was some related work of Kichlu where he uses kind of spectra with weight filtrations and kind of models the situation, but I'm not sure I fully understand the construction.
And what about the co-homological degrading?
Yeah, so you have co-homological and the weight filtration. These are like Q and T.
Okay.
Yeah, so A is equal to 0, you're on one level of A filtration, but Q and T are co-homological degree and the weight filtration. That's right.
It's like the mixed type problem.
Yeah, yes.
Any other questions?
One easy example, which I can say maybe in words, is that so for the Hopf-Link, for example, the variety that you get is that you take C2 and you remove a hyperbola, xy is equal to 1. So that's an open algebraic variety, and you can compute homology by many ways, Alexander duality, whatever. But like this is like for the Hopf-Link, you just have C2 minus hyperbola. It's very easy. For trefoil that I was showing on the slide, it's slightly more complicated space, but I mean, you can compute its homology in that case directly without knowing any of this theory. And you get, the first time you get interest in weight filtration is this 3-4 example. And again, this is this Petitroid variety in Grassmannian 3-7, or it's so-called E6 cluster variety for E6 cluster algebra. And cluster people have computed its homology. And like, it's remarkable that from this very different perspectives, you get the same result at least. But maybe that's too technical. Yeah. There is a long paper of Thomas Lam and David Speyer when they discuss these examples, although again, it's kind of hard to recognize this example. But I think if you want to read more about this, so either like look at the papers that I mentioned, and this paper of Galashin and Lam like is very explicit, and like they write everything like super explicitly what's going on, what are the filtrations, how does all this work out examples. So I think this is really good paper.
Any other questions?
Yeah, Eugene, I have a question.
Uh-huh.
So it's kind of a vague question, which is what makes the delta grading so special? Is it really just the sort of these like SL1 differentials, or is there some other, like, are there some other interesting operators which sort of preserve delta grading? Or
I mean, you have SL2, which preserves delta grading, and you have a D1 differential. Yeah, and you have SL1 differential, which preserves it. And so you can use SL2 and this D1 differential to kind of take the symmetric differential. So this would be D-1 for G. And then you can ask, like, what is an interest in algebra? What are the commutation relation between these things?
all right, wait, so you have this SL2 even for reduced homology. So we were,
yeah, SL2 you have for knots, you have it for reduced homology, of course.
yeah, okay.
So but like, I mean, the point is that you can ask, are there more operators? I don't know, but you can just ask, for example, is it true that differentials commute with SL2 or not?
Yeah.
Or like the spectral sequence can use with SL2 in some appropriate sense, and I don't know even in which sense. But like D1, I think so. You can take the commutator, that would be kind of D-1, and so you have like, maybe I'll show you. Where was this picture? Yeah, that's a nice picture. So for example, this whole block you can actually understand pretty easily, because on the top you have an irreducible SL2 representation. Then you have this differential which goes from here to here. And you know that like on this level, you don't have any homology for D1. Like S invariant would live here, actually. And so this is your D1. And then it goes this. And then here you have an action of SL2, so you can actually draw the dual differential. And then you kind of go down. And so you can describe this whole picture just by knowing kind of SL2 representation on the top and D1.
Awesome.
And so, yeah, I mean, that's kind of the question if there are like more interesting algebras going on here and like more interesting structures, but I think it's all wide open and very, very interesting. Yes. But yeah, I mean, one thing is that SL2 definitely preserves delta grading, definitely acts in reduced homology Fanos. And
Yeah.
forget about the links for a moment, just like what actually acts there and like what happens. What are interesting homological operations? That's all very interesting question.
Mhm. Cool.
There is also a question about Homology homology, Higger-Floer homology, which how this is related to Higger-Floer, but maybe let's not talk about this.
Yeah. So this like this
Yeah.
expected differentials
Yeah.
that preserve delta gradient that would decrease.
That
delta.
would move the delta gradient. No. Like D2
Why,
also.
why not talk about it? It's too complicated.
Yeah. Okay.
I just don't know what to say. I guess that's the honest answer. But like, I mean, you would have the differential D2, which would go, I think, from here to here, if I remember correctly. So that would be SL2 differential. So that would be kind of D2 for kind of n is equal to 2. But in principle, you can try to mix it with SL2 action. You might get some other interesting differential. So conjecture, yeah, maybe. So this is the picture for all differentials for torus knot. Again, taken from this very old paper of Khovanov and Anton Mellit. So the D1 differential, which kind of for the Lie spectral sequence is this one. So 3 goes to 2, 5 goes to 4, 8 goes to 7. And then I kind of pointed this 7 to 6. So these arrows in this direction is D1 differential. And the only surviving guy is this one. Then this longer arrow is D2 differential, which goes from here to here and here to here and here to here. Yes. And so you can compute homology of that in this example, and that give you Khovanov homology. And then there is also this vertical differential in this case, which give you Higger-Floer homology. In this case, it's just there. But in general, yeah, I guess I don't even know what's the status of all the spectral sequences from HOMFLY homology to Higger-Floer homology. But people have been definitely working on that. And so you can ask how that differential fits into this picture, and I don't know. But in this example, yeah, it's definitely true and it works. So you have vertical differential, and this would be your Higger-Floer spectral sequence. And again, you can ask, like, you have like zoo of these differentials, how they interact with SL2, which acts horizontally, how they interact with each other, even if like you have only one differential in the spectral sequence. And I think there are lots of questions that one can explore, basically by comparing this data with Higger-Floer and Khovanov and like trying to guess what the actual differential is.
Thanks.
Any more questions? If this is not the case, yeah, let's thank Eugene again.
All right. Thank you so much for having me.
Thank you.
Thank you. Do you want me to send you the slides?
That would be great. Yeah.
Yeah, okay, I'll send you the slides then.
Okay.
Okay.
Thank you.
All right.